All right, class, we're going to start Chapter 5 today. Chapter 5, we're going to continue talking about polynomials, but we're going to look at this idea of factoring. Now, if you go ahead and open your book up and look at the table of contents, we're going to see Chapter 5 is really long. We've got 13 different sections, and we're going to do each section in Chapter 5. We're also going to see that Chapter 5 is broken up into 4 shorter sections, and so that's what we're going to start working on today. Now, let's everybody go ahead and open in your books, and let's look at page 185, and you're going to see here the idea is factoring integers. Now, let's review just a little bit. What is an integer? Remember, if we're dealing with integers, then we have positive numbers and we have negative numbers. We learned that integers are numbers and their opposites. So that's how we've got positive numbers and negative numbers. So if you know your multiplication tables well, this first section should be pretty easy for us. Now, if you look at example 1 in your book on page 185, they want us to give them a list of factors, okay? A list of factors. So if they wanted me to give them the list of factors for 12, I would have to give them all the numbers that are multiplied together that equal 12. Now remember, a factors are two numbers that when I multiply them together give me the desired product. So if I wanted a list of all the factors of 12, we're going to give me a list of numbers in numerical order. So it'd be 1, 2, 3, 4, 6, and 12. Okay? So when they ask for the list of all positive factors of a number, okay, we give them a list in numerical order. How about if they wanted a list of factors for 42? Well, I'd have to think about that one for a little bit. Sometimes when I have to think, I need 1 in 42. Now, will 2 go into 42? Yeah, that's going to be 2 and what? 21. Will 3 go into 42? It sure will. 3 times 14. 4 doesn't go into 42. 5 won't go into 42. And then we know 6 times 7 is 42. So knowing your divisibility rules is also another good thing to have on hand to help you as a tool to get through this. Okay, so the first thing they're going to ask is, hey, what is the list of all the positive factors? Now, the second thing that they could ask us, if you look at example number 2, is they're going to say list all pairs of factors of each integer. Now, because they put that word integer in there, we've got to realize that integers means positive numbers and their opposites. So if you look at example A, they want all the list of pairs for 18. Well, I know that that's going to be 1 and 18, and it could be 2 and 9, and it could be 3 and 6. Okay, there I've got 3 pairs of factors for positive 18. But because they said that word integer, that means it could also be negative 1 and negative 18. Because I know from chapter 2 that a negative times a negative is a positive. So instead of 3 pairs of integers, I actually have 6 pairs of integers because I need to give positive numbers and negative numbers. Now let's switch it up. Let's say instead they wanted me to give them, okay, the list of integers, okay, for negative 18 instead. Well, this time I need a negative number. Now, in order for me to multiply numbers together to get a negative, remember, one has to be positive and one has to be negative. So this could be negative 1 and 18. It could be negative 2 and 9. And it could be negative 3 and 6. but there's also another 3 more pairs of integers. Basically, I just switch the negative sign. This could be 1 and negative 18, and this could be 2 and negative 9, and 3 and negative 6. So if you notice there, I still had 6 pairs because I have to take into account the idea of integers, positive numbers, and negative numbers. All right, so let's go ahead and go to our next slide. Let's see if we can do numbers 1 and 2 together. All right, let's look at number 1. What would be all pairs of factors over the set of integers for 57? Well, I know it's got to be 1 and 57. Okay, will 2 go into 57? Nope, it's an odd number. Will 3 go into 57? I think that works, and that's going to be 3 times 19, and I think that's it. 4 won't go in there, 5, 6, I think that's it. Okay, now that's only my first 2. There's actually 2 more sets of integers. Do you remember what they need to be? Yeah, that's right. I need -1 and negative 57 and negative 3 and negative 19. Now, let's look at this idea again for negative 52. Well, I know it's got to be -1 and positive 52. Will 2 go into 52? Yep. So it's going to be -2 and 26. Will 3 go into 52? Let's look at that in 5. No. Okay, will 4 go into 52? Yes, 4 will work. It's going to be -4, and we're going to get 13. Okay, now that's my first 3 sets of pairs of integers. I get 3 more sets, and how I get the next 3 sets is I just flip the negative sign to the other factor. All right, so when they want me to give them the pairs of factors over the sets of integers, that's when I've got to worry about positive numbers and negative numbers. Now, we've got a special case of numbers that we have yet to talk about, and the idea here is the idea of prime numbers. Who remembers what's a prime number? Yeah, that's right. A prime number is any number that the only factors are 1 and itself. And so we did a lot of this last year. We looked at the idea of prime factorization. Now, there's actually 2 different methods. One method is called tree, and the other method is called cake. Personally, Mrs. Burton doesn't care. Just get me the right answer. So let's do 120, and let's use the tree method for prime factoring. If I was going to use the tree method, well, the first thing we need to come up with is 2 numbers that I can divide to get 120, and I like to start with prime numbers, and 2 is a prime number. So does 2 go into 120? Yes, and it's 60. Now I like to circle the prime number when I find it, so it's easier to go back when I'm coming up with my exponents for my repeated factors. And then I look at 60. Well, 60 can be what? 2 and 30. 2's another prime number. Okay, 30. Well, that can be 2 and 15, and there's my prime number. Now when I get to 15, 2 won't go into 15, but 3 will, and that's 3 times 5. Okay, so when I get to a prime number, I circle it, and now use exponents for repeated factors. How many 2's do I have? 1, 2, 3. We're going to say 2 cubed times 3 times 5. Now, let's say I was going to use the cake method. The cake method, in my old school, we called it upside down division. So we're going to do the same number. Instead of the tree method, though, we still use the same idea. What's the lowest prime number that will go that is divisible by 120, and that's 2. Well, 2 goes into 120, 60, and I keep using that same factor, prime factor, until it won't work again. Well, 2 will go into 60, that'll be 30. 2 goes into 30, that's 15. 2 won't go into 15, so my next prime number is 3. 3 goes into 15 5 times. Well, 3 won't go into 5, but 5 will, and you keep going until you get a 1. Okay, now, So let's look and see what our prime factorization is. We're looking at all the numbers on the side, and we've got 2 written 1, 2, 3 times, so 2 cubed times 3 times 5. So if you notice, it doesn't matter the method that we use, whether we use the tree method or the cake method, we still get the exact same answer. All right. Now, what would happen if I wanted you to find the GCF of a group of numbers? Now, we're going to actually start with one with a 2 for all, and let's do these 2 numbers. Let's say I had 28 and 70. Now, here's where I really like cake, because I like to take care of double cake. If I look at double cake, well, my smallest prime number is 2. 2 goes into both of those. 2 goes into 28 14 times, and 2 goes into 70 35 times. Now, next 2 will go into 14, but it won't go into 35, so I can't use it. Okay, the next prime number after 2 is 3. 3 doesn't go into either 14 or 35. The next prime number is 5. Well, 5 works for 35 but not 14, so I can't use it. After 5, the next prime number is 7. 7 goes into 14 2 times, and 7 goes into 35 5 times. Now, when you get prime numbers down here on the bottom, we're done, but it's the 2 here that we're going to multiply together, and so the GCF of those numbers is 14. So how about if we did a 3 for all? How about if we did the 3 for all? Well, look what happens. If I do my prime factoring of each one of those, all right, here we go. And now when I look at the numbers, what number is common, GCF, greatest common factor? Well, if I look, 2 is not, okay, I've got a 2 here and a 2 here, but I don't have a 2, so 2 is not a common factor. 3 is a common factor, okay? 3 is the common factor, and so we're going to take the greatest common factor, so it's going to be 3 squared, because this one has 1, this one has 2, and this one has 1. Okay, so it's going to be 3 squared. Now, I've got a 5, but not in all 3, and then we've got a 7. So we've got 9 times 7, which is, oh, I think I did that wrong, gang, because I am a cake person. All right? Let's go back and look at cake. I can take care of cake better. If I have 105, 126, and 210. Well, when I look there, okay, 2 won't go into all those, but 3 will. 3 goes into 105 how many times? 35, I think. Yep. 3 goes into 126 how many times? 42. Okay? And then 3 goes into 210, 70. Okay? Now, 2 won't go into those again, but 3 won't go into those again. 5 won't go into those again, but 7 will. 7 goes into all of those. All right, so this is going to be 5, and this is going to be 6, and this is going to be 10. All right, and I think we're done. All right, so again, we've got 2 times 3, which is 21. So let's go back up here and look at this idea of, so when I look here then, 3 is common to all 3. 7 is common to all 3, so we end up with 3 times 7, which equals 21. Okay, so tonight's homework, you're going to find list of factors, pairs of factors, and greatest common factor. Good luck.